Welcome back, class. Engineering mathematics. Today we'll be discussing differentiation. We've already discussed the applications of the fundamental theorem, which we derived using the graph, where I took dy over here and dx over there, and took dy by dx and explained it as slope of a very small element. We described the element as a very small part of a big thing, and we defined integration as integrating the small elements to get back the main big thing. Other than that, we also discussed the use of the fundamental theorem of calculus, that is limit h tending 0, fx plus h minus fx over h gives us dy by dx, dfx by dx, sorry. And we also thought about different differentials like polynomials, trigonometric, logarithmic, exponential, etc. Hope you understood all that stuff and you do not have any problem, because today we will be continuing our study of differentiation, and we will study different rules by which you can use differentiation to calculate the slope of functions. And we'll also discuss some applications of differentiation, where is differentiation used and how do you use it to your advantage, etc, etc. Now we'll start by learning the sum rule, sum and difference rule. It is said that differentiation respects sums and differences. So what do I mean by this? I mean that we are going to differentiate y is equal to u plus minus v. We are going to differentiate y is equal to u plus minus v. Now, if we take y as fx, u as, let's say, ax, and y as bx, and I can write that fx is equal to ax plus minus bx, ax plus minus bx. After that I can continue to, now since I have to find the derivative of fx, and I know the formula is f of x plus h minus fx over h, limit h tending whole of limit h tending 0, I can put that dy dx of fx is equal to limit h tending 0 gx plus h plus minus h a plus x plus h plus minus minus f or g of x minus g of x plus minus plus h of x, limit a tending 0, like I've written over here. Now if we separate them, we get, when I separate them, I do limit a tending 0, g x plus a minus gx over a, and plus minus limit a tending 0, h of x plus a minus hx over a, which gives me that d of fx over dx is equal to d of gx over dx plus minus d of hx over dx, d by dx of hx. So what do we come to know here? That if y is equal to u plus v, dy by dx is equal to du by dx plus minus dv by dx. So if it is y is equal to u plus v, dy by dx equal to du by dx plus dv by dx. If y is equal to u minus v, it is dy by dx is equal to, yes, yeah, du by dx minus dv by dx. Excellent. Now, this was the sum and difference rule. Now let's take some examples on sum and difference rule. which are very important. We'll now differentiate an actual polynomial function like y is equal to, let's take y is equal to x square plus 3x plus 2. Y is equal to 3x square plus 3x plus 2. Now I can write it as y is equal to u plus v plus w. Okay, and dy by dx is equal to du by dx plus dv by dx plus dw by dx. So dy by dx is equal to du by dx, which is 2x, which is 2x, plus dv by dx, which is 3, plus dw by dx, which is 0. Differential of a constant is 0, and for the first two parts I've used the power rule, the very important rule, that d by dx of x to the power n is mx to the power n minus 1. So I get this as dy by dx is equal to 2x plus 3. Or I can say that dy by dx is equal to 2ax. If I use a general polynomial equation, y is equal to ax, not general quadratic equation, y is equal to ax squared plus bx plus c gives me different dy by dx is equal to 2ax plus b. This is a very important result, and we'll be using it to actually define what we call as roots of a polynomial, and when a polynomial has roots and when not, and when is the polynomial maximum, when is it minimum, when is it not changing, and when is it constant, and all that stuff. Continuing ahead, we have I want to similarly we can use the difference rule. For example, if someone tells us to differentiate tan theta minus cos theta by d theta, y is equal to assume y is equal to tan theta minus cos theta, and someone tells us to do dy by dx. So how do we do it? We take tan theta as u and cos theta as v, and we do y is equal to u minus v. d by dx of y is equal to d by dx of u minus d by dx of v. It can also be thought as d by dx of minus 1 into v, which is very right. So over here I take dy by dx is equal to d by dx of tan theta, which is sec squared theta, minus differential of cos theta, which is minus sin theta, and we get secant squared dy by dx is equal to sec squared theta or secant squared theta plus sin theta. Secant squared theta plus sin theta is our differential of tan theta minus cos theta, and you are given the worksheets in the notes. There are some more questions to solve, some more interesting things to use, like use some trigonometric equations and then solve them. For example, if I say find dy by dx, this is a very important thing we are going to do now. dy by dx of sine squared theta plus cos squared theta. Now these are functions being multiplied. We currently don't know a rule of multiplication, but we know that sine squared theta plus cos squared theta is equal to 1. So we just put dy by dy is equal to 1, so dy by dx is equal to 0. We will soon derive that this dy by dx will be 0 after we've gone through the next rule, which I want to introduce, that is product rule. And we'll also see how product rule is very important. Product rule is as important as the sum rule and difference rule, if not more. What we'll do in product rule is, we have y as a function of ax into bx. Fx is a function of ax. Fx is defined as ax into bx, if you can see it clearly. which shows how fx is defined as the sum of ax and bx is the product of ax and bx. Now if we use the same formula, we calculate the limit, and we get, using the fundamental theorem, we get that we get d of fx by dx is equal to limit h tending 0 fx plus h minus fx over h. We substitute the value of fx and we get the answer as I don't think you can read it clearly over there, but it is saying that limit h tending 0 ax plus b into bx plus b x a into a of x plus h into b of x plus h minus a of x into b of x all over h. That is what we are given there. Continuing with that, I will continue over here with that. I haven't written that. It is limit h tending 0 bx into a x plus h minus ax over h plus b plus a of x into bx plus h minus bx over h, limit h tending 0. This gets us to a conclusion that d by dx of fx is given as ax d by dx of bx plus dx into d by dx of x. You might be able to see it correctly if I put it over here, I think. Can you see it correctly? I hope you can. If you can't, I'll just repeat it. Is this saying that d by dx of f of x is equal to d by dx of ax into bx plus d by dx of bx into ax. It's even given in the notes if you want to check at uchit07.wordpress, that is wordpress.com. If you go to about the lecture series in that black area, you can actually see all the lecture notes for these lectures that I'm giving you. It's kind of lecture, I should say, not lectures actually. Okay, moving ahead, we have division rule. Before I move into division rule, I want to go back to power rule. It said x to the power n. Let's see if it's x into x, and if we use the product rule, what answer do we get? Product rule for x into x says that if y is equal to x into x, then dy by dx of it is equal to x into d by dx of x plus x into d by dx of x. That means 2 times x into d by dx of x. D by dx of x is obviously 1. We know that. So we get dy by dx is equal to 2x. Same answer as the one we got for x squared. If we do it for x cubed, we get x into x into x squared, I should say. So I won't use the form power rule over here, so this is how I'm going to do. So I do y is equal to x into x squared. So I will do y is equal to x into u, where u is x squared, and so y is equal to u times d by dx of x plus x times d by dx of u. And now dy dx of u can be calculated from what we calculated up here, that's u is equal to x into x, du by dx is equal to 2x, dy dx of x, which is 2x. And if I put 2x here, I get this is x, this has x, that's x squared, and this is x squared, this is dy dx of x, which is 1, and this is 2x squared, 2x into x, which is 2 times of x squared. So that's 3x squared, and same as the one we derived for the power rule, 3x squared. Now we don't stop here, we continue moving. We derive the, I promised you I'll show you sine square x plus cos square, sine square theta plus cos square theta. So y is equal to sine square theta plus cos square theta. We say y is equal to sine theta into sine theta plus cos theta into cos theta. U is equal to sine theta into y is equal to u plus v, where u is equal to sine theta into sine theta plus, and v is equal to cos theta into cos theta. So first we do it for u. We apply product rule. We get du by dx is equal to cos sine theta into d by dx of sine theta, which is cos theta, sine theta cos theta, because that, plus dy dx of sine theta, which is cos theta, into sine theta, which gives me 2 sine theta cos theta, 2 sine theta cos theta. I won't do anything here, even though you know what you can do from here. You can do it as sine 2 theta. And if I move to the v has cos square theta, that is cos theta into cos theta. Solving that, we get cos theta into minus sine theta plus cos theta into minus sine theta, that is minus 2 sine theta cos theta. Dy by dx is equal to du by dx plus dv by dx, that is dy by dx is equal to 2 cos theta minus 2 cos theta sine theta minus 2 cos theta sine theta, and we all know it's sine 2 theta minus sine 2 theta, which is 0. And one more thing, just remember the integral, the differential of sine square theta is sine 2 theta, and the differential of cos 2 theta is cos squared theta. Sine square, the differential of sine square theta is sine 2 theta, and the differential of cos square theta is minus sine 2 theta. So we again got a 0 as the answer, and that proves our theory before, that we can even use the rule. So if you do it like this in the exam, you waste time. You have 1.5 hours to give a 100 marks paper, and if you are wasting time doing the y is equal to sine square theta plus cos square theta, the differential, then I think you will be wasting a lot of time. And plus you won't be given questions like this. This will be a part of a very bigger question for like 8 marks or so. We won't think about those questions right now. We'll obviously think about them later, but not right now. Moving on to quotient rule. Quotient rule is given as what will be the differential of fx if fx is defined as ax over bx, and that is ax over bx. What will be the answer? Ax over bx. We again use the fundamental theorem of calculus, and we get d by dx of fx is equal to limit h tending 0 a of x plus h over b of x plus h minus b of a of x over b of x over h. That gives us our equation, and cross multiplying equation, we get limit h tending 0, we get ax plus h times bx minus ax bx plus h minus bx plus h over dx bx plus h into h. So if I take this as 1 over bx plus h, limit h tending 0, I just separate this part off into this other part, which is ax plus h bx minus ax bx plus h. Then I will get this as 1 over b or bx squared as the denominator into ax plus h bx minus ax bx plus h, and that can easily be simplified to give us the equation which we want, which is the same way we simplified for the product rule. And the equation we get is fx, if fx is equal to ax over bx, then dy dx of fx can be given by the following equation, which is dy dx, which is bx into dy dx of ax minus, now this is minus, just remember that in the earlier equation we had a plus over here, but this time this is minus, minus of ax dy dx of bx all over bx squared. Remember the bx squared which we had got earlier before, bx squared. You can see the equation is given in your notes though, so you don't actually need to read it over here. It just says dy dx of fx is equal to dy dx is equal to bx into dy dx of ax minus ax into dy dx of bx whole divided by bx squared. It's very simple to read and see and use. Now we know that the differential of tan theta, we use the differential of tan theta is equal to sec square theta, but I want to show how that thing can be derived. How can it be derived that tan dy dx of tan theta is sec square theta? And that's what we are going to do right now. We say that fx is equal to tan theta. We assume that fx is equal to tan theta. We say is equal to sin theta over cos theta. Cos theta, we all know this thing that tan theta equal to sin theta over cos theta. Now we can say that f of x is equal to ax over bx, where ax is sin theta and bx is cos theta. Now simply using the earlier formula, we get that f prime x is equal to cos theta into differential of sin theta, which is cos square theta, minus sin theta into differential of cos theta, which is sin square theta, over cos square theta. Cos square theta plus sin square theta equal to 1, we know that. And 1 over cosecant square theta is equal to secant square theta. And this is how we derive. Please have a look at it. If we got f prime x is equal to cos square theta plus sin square theta over cos square theta, which is equal to 1 over cos square theta is equal to sec square theta. So we derive that differential of tan theta is sec square theta. So that means our this formula of division quotient rule is correct. Now moving on to the most important rule in differentiation. This is the rule which we'll mostly be using much more than the even the addition, subtraction and multiplication, division rules. This is called the chain rule. In this you keep building it's called a chain rule due to some very Newton called it the rule of differentiation. That's the importance it is. It is more important than the fundamental theorem of differentiation. This is what actually makes our things correct. Differentiation actually easy. This is like it was and it was called chain rule because when we go into very high complexity, that is when we have many functions overlapping each other, they form like a chain. They form a chain around the inner central function, and to solve it you have to start from the out of the chain and reach the inner part of that chain. That's why it's called chain, so that you know that you start from outside and go in rather than start from in and go out. That's not allowed. You can't go in to a chain without opening the outside of the chain. Obviously, that's why it is called the chain rule, or how Newton called it, the differential rule. The differential rule is very important because it helps us come to know that how a given function is going to be differentiated. Usually we don't encounter very simple functions. We encounter functions like having like h is equal to lambda by l. Wait a second. Hello? Yeah. In my room. Yeah. I think the controller. Okay, after 5 minutes. Okay. That was just an important call which I had to attend to. I'm very sorry for that. Where was I? Yeah, I was at chain rule and explaining why chain rule is so important. Chain rule is important because it helps us come to know how to differentiate very complex functions. Like only yesterday while teaching you heat transfer, we counted the equation of h is equal to lambda by L, bracket starts, r e to the power 0.8 minus 0.0028 r e to the power 0.8 minus 275, and then r e Reynolds number to the power 0.8 is not very simple because it is rho u d by mu to the power 0.8, and all of them are dependent on each other, and if I give you one differentiate in respect to one, you have to go very complex. It will go very complex. So that's why we use what we call as chain rule. If fx is given as a function of gt, okay, if fx is equal to gt, that is, if y is equal to fx, and let's say y is equal to sine t, y is equal to sine t. Now you have to find dy by dx. Now, over here I wrote t. Actually, I should have written it as g of. Actually, I should write it like this: f of x is equal to g of hx. If f of x is equal to g of hx, as you see there, then there's a problem. Or we write it as fx is equal to g o h x. This circle is very important. The circle over here is very important. You encounter it in many places. This circle between g and h, it says that g of hx. So it take hx and do the g of it. For example, if g is sine theta and hx is x squared, then it says take x, first do x squared, okay, and then put it into sine theta, so it becomes sine of x squared, something like that. So actually exactly like that, but different examples. So what happened was, in terms of chains, and since we are discussing chain rule, in terms of chains, what happened was that we started from the inner link and built an upper link by taking x and then x squared. We made one link, then taking sine of it, we made another link. Now let's say it was cos or sine of x squared, then we make another link, and then another link, and then another link, and so on till infinity. But thank God you won't be given problems which have links till infinity. That is x sine, let's say sine cos of tan of log of e to the power minus sine of cos of tan of x cubed plus 6x plus tan x plus 3 rho x 3 of infinity. I mean, like, it can be anything. You can differentiate almost. You can differentiate not almost. You can differentiate any possible function. Any possible function can be differentiated using a simple chain rule. Chain rule allows you to differentiate any complexity of a function. All you have to do is start at the outer link of the chain, end at the smaller link of the chain, and that's it. Now what is chain rule actually? What chain rule actually is it is, if I want to find d by dx of fx over here, which was g of hx, then I take d by dx of fx and say that this d by dx of fx is equal to g or d by dx d by d hx of g of hx into d of hx by dx. Now what I mean over here is that the differential of fx is actually that differentiate this outer link with respect to the inner link, then you multiply it by the differential of the inner link with respect to the second inner link, then you multiply it by the differential of second inner link to the third inner link, then you multiply it by the differential of third inner link to the fourth inner link, and so on until you reach the last link where you have x as x, like x squared or something like that, where is function of x actually, where it's actually a simple function of x, the ones we know how to differentiate. Until we reach that, we keep doing this multiplication, and if you see here, what I've written here is the most important rule, which is also called the differential rule. This is very important and is also termed as chain rule. And this rule, if you see over here, I've written d of fx by dx is equal to d of gx by d of hx into d of hx by dx. That's because gx was the outer link, hx was the inner link. So we differentiated this with respect to this, and then we differentiated this with respect to x, because this was a function of x and not a function of another function. Function of another function is very important. It is of utmost importance to engineers, so it is of utmost importance that you know what chain rule is. So what is we took fx as sine x squared. So if I say that d by dx of fx or f prime x, if I want you to find f prime x, what is f prime x equal to? F prime x will equal to simply sine x squared d by dx of sine d by dx squared of sine x squared into d by dx of x squared by dx. Do you understand how I did it? I hope you do. But if you don't, it's explained also in the notes, so you can see it. Over here I don't have a chalk or a blackboard, so I can't show you. You can only see my motion of the hand, which I'm doing over here, and I'm writing it as cos x squared plus into 2x, or 2x cos squared x. 2x cos squared x is the differential of sine x squared. Now we'll do some more complex differentials, like sine of cos of x squared. What is the differential of sine of cos x squared? It's simply, I told you, start from the outside of the link, that's the top link. So we start from the sine part. Differential of this will become cos of x squared into minus sine of x squared into 2x. So it becomes minus 2x sine x squared cos of sine cos of x squared. So it was sine of cos of x squared. So we get cos of x squared. Now what I want to tell you is, how do you differentiate e to the power sine squared x? Now this is tough. How do you differentiate sine squared x, huh? We discussed sine squared x by product rule. Now I want to discuss it by another rule. I say that dy is equal to sine squared x. I can say y is equal to sine x squared. So if I take sine x as hx and squaring as gx, it's a kind of chain rule only. So what I do is, I do y is equal to 2 sine x, that's product rule, into cos x, and this gives me cos sine 2x. So chain rule helps us get that answer so quickly. So again, if you're given some function like e to the power sine squared x, and when you read sine squared x, you're applying over here. How will you do it? It's simple. It's simply e to the sine 2x into e to the power sine squared x. If you want the answer, the way to do that answer is given in the notes. Do check it out, please. As you say, please do check it out, because it is important that you understand how you do this. Some more functions, for example, tan of sec x. How do you differentiate tan of sec x? You write it as sec squared of sec x into sec x tan x. So you write it as sec x tan x, sec squared of sec x. Okay. Sec x tan x, sec of sec x into sec of sec x. I think I've done a lot for today. You need to rest. You have the assignment in your notes. You should try completing that assignment. And for now, let's say goodbye.